My name is Jeff Newmiller. I work for DNV as a solar consultant, specializing in energy modeling. So I'm going to talk a little bit today about the history of ASTM capacity testing to put into context why I'm proposing this method for bifacial capacity testing. There's more to the capacity test than I can present in 20 minutes. So I'm going to focus on why and the measurements a little bit. So I guess this is part one, to be continued in the future. Here we go. All right. So got another scope of the day and the foundations of ASTM 2848, and possible adaptations that I have seen, and why each one, I don't know, has some advantages, has some disadvantages, and hopefully afterward, maybe we can discuss various opinions on that. And I'll kind of wrap this up with a brief review of some field data that was collected at NREL. All right. So the scope of the work here is I'm just today trying to talk about the impact of bifaciality. What does it do? What does it change about capacity testing? And how do they align? I mean, how do these measurements align with intermediate results? There are a number of ways that you can try to create an alignment between what you see in the field and what you've got in your model. And ASTM has a history of primarily focusing on like POA irradiance. It's kind of this generic POA irradiance, but there's a lot of subtleties about how that could potentially be measured. But as has been mentioned earlier today, the goal is basically to say, under reference conditions, what would be the power coming out of the system? It's worth noting that the point of comparison is a model, and that the model is probably imperfect. It is what we had available, what the modeler decided covered enough of the bases to get a reasonable answer without being too excessively detailed. But as we go forward in time, PVSys improves, our work brings more improvements into the modeling process. Those improvements were not available in the past, and whatever improvements we come up with in the future aren't available today. So we're always comparing with an imperfect model, and it's worth noting that that's what we're actually doing with a capacity test. It's trying to say, we said we would do this, can we do it? So monofacial testing has a real-world side and a modeling side. The real-world side is described in ASTM 2848. The modeling side is described in ASTM 2939. The intent is that you use your model in a way that allows you to pick off some values that can be compared with what you see in the field. PVSys has an easy glob-ints measurement of POA that can be compared with a broadband pyrometer mounted in an unshaded, unobstructed area. And that's kind of the basis for how the test was thought of. It sometimes gets modified to use things like reference cells for situations like for solar, where they're concerned about large spectral impact. But the basic principle has been that the site owner doesn't care whether you come through the door with a PV module that is really good at converting infrared light. They know they have a certain amount of broadband light. What can you do with it? Figure that out. So the results obtained are not always as precise if you pick these rough measurements of irradiance and simultaneously your model isn't correcting for all the little fine details because you took some shortcuts. So you can in general get a more a slightly larger uncertainty when you're using a number like glob ints as opposed to using a number like glob EFF. I'm going to also point out, and this is kind of relevant, is that ambient temperature is part of the ASTM 2848 because if you take a PV system and you mount and you install it, and lo and behold, there's no ability for air to get in the back, but your model assumed that plenty of air could get back there and cool it, then the module will be hot. So you can get an accurate answer by measuring the module temperature and say, yes, the system is performing as expected, but you will overlook the fact that the modules may be operating 20 or 30 degrees hotter than you had intended them to be. So ASTM takes this view that we're going to use the ambient temperature and the wind speed to capture that potential failure. I don't necessarily think that every project needs to use the strict ASTM equation with ambient temperature, but wind speed has this effect that has been, there's been a number of papers that have said wind speed doesn't actually reliably change the answer, but a basic fluids class will always talk about the free stream flow, which in our case, we would assume is a 10-meter high anemometer. If you put the anemometer at the elevation of the modules, you'll experience a lot more turbulence, and it'll be harder to see what's actually going on in that turbulence because you're so in such a localized position, you can't see the average behavior easily. So PVSYST usually assumes that you're using some kind of a 10-meter wind speed, and it's very frequent for systems to be installed with a 2-meter high anemometer, which tends not to work very well. But I'm bringing this up because if you go to a measurement point that gives you a stable answer, you can often see the average behavior more clearly than if you try to get into a detailed point and start seeing, details that don't apply to the whole system. And that's really where I come into saying, let's take an outboard measurement instead of sticking a sensor, a pyrometer underneath the array amidst these complex shading situation, put it outside the perimeter of your array where the irradiance is more stable, and you will end up with a bias, but you can account for that because this is a capacity test and it uses regression, so it can adapt to that bias. I'm also the GHI. There's a principle. The owner says, I don't know what POA is going to be, but I have a sensor I can stick out there for GHI. But the accuracy of irradiance decomposition and transposition is it's at best, kind of going through the middle of a very inaccurate model of transposition. You could have, a continuous cloud sky. You could have a bright spot over here. They have very different diffuse light behavior that when you tilt it up gives you a different answer. So transposition is a very imprecise thing. And when they were developing ASTM 2848, they gave up on the idea of wrapping the failure or success of the model to do that transposition properly. But they did not give up on everything. They went and kept the ambient temperature so that they could capture some things. It was kind of a compromise. Okay. The effect of bifaciality at the cell level, there are impediments to the light reaching the active material from behind that are not as present on the front. So you have an asymmetry as the bifaciality factor. But that is characterized at the module level. And when you put it into the PV system, the installer could easily put large structural beams that obstruct the light from getting back there, or they could be spaced out differently. And it's quite a complex situation to be in. There's no stable position you can go to identify this value directly without also bringing in the fact that there's these structural shading issues as well. So when you ASTM 2848 is a system level evaluation, and my goal is to try to continue to address the fact that on the front side, you would put the sensor in an exposed area and leave it to the model to figure out how much less irradiance is going to reach, say, a part of the surface that's closer to the ground. The rear side has similar kinds of constraints. So one way to deal with this is just to kind of pull out your hair and say, ignore it. I'm just going to test this with a standard ASTM test that only looks at the front side irradiance. What'll usually happen then is that you'll have an expectation that less power is going to come out because you modeled it as monofacial, and more power is in fact going to come out because it is bifacial, and the EPC is going to be happy because they were going to get more power out and pass the test 99.99% of the time. But the investor feels a little bit left out in that particular exchange and will often come to the door and say, Mr. Developer, you're going to have to take the risk and do the test again. Now you've got 2 tests. But omitting the test can actually make sense if your bifaciality boost is really small, which can happen if you cram the modules really close together, or if you have a really low bifaciality factor. So in those cases, the actual bifaciality boost could well be, less than 1%. And your measurement accuracy is not going to be able to identify that. So the wisest course in some cases may simply be to omit considering the rear side irradiance. Another possible thought that has been raised is, look, if the sun is bright, the rear side is going to be bright. If the sun is dim, the rear side is going to be dim. That's often justified by looking at this equation, which was presented before, and just calling this first term the bifacial irradiance factor, and then forgetting that the bifacial irradiance factor changes throughout the day. So I've seen capacity tests constructed to say, let's figure out what the bifacial irradiance factor is, and then just adjust all the front side irradiance measurements. So that doesn't do a very good job. All right. Let's put sensors in the plane of the laminate, right where the cells are. So you take 2 modules and you push them apart a little bit. Now modules have frames, so that means they have some metal projecting out. You put your sensor in the plane of the laminate, and now the sensor field of view sees the module frame. If the module frames are large, it'll see a large obstruction of that. If they're small, it'll see a small obstruction. In a sense, it becomes insensitive. It's the same kind of situation as with using module temperature instead of ambient temperature. Who cares if they put large frames on, or purlins that are excessive and causing an increased shade and reducing your bifacial capacity? So there's a problem then with simply putting it at that level. Then there's this question of how does it vary? I mean, in the middle of a module, those 2 frame bars are quite far apart. If you're between two modules that just got shoved 4 inches apart so you could stick a sensor in there, they're quite close together. So locally, there's a shading situation that isn't representative of the entire backside of the array. So, okay. Further, Ken McIntosh showed some simulations that suggest that there's a complex field of speckled irradiance, bright and darkness that's changing on the backside of a tracker throughout the course of the day. So no single place that you put it actually is going to be representative of the average. So even though we had discussions earlier that said, 55% away from the torque tube could be appropriate for a 1P arrangement, that's really only valid when you're looking at an energy basis of evaluation. Throughout different times of a single day, that bright spot could move back and forth. And so there's no one spot that you can put any sensor back there that's going to give you the right answer all day long so that you can complete this test in a 2 or 3 day period. Another idea is using a reference module. So a reference module says, I'm not going to try to measure them separately. I'm just going to give you, say, a short circuit current out of a module that is the quote same as the rest of the modules, which is fine as long as they are the same, as long as they're exposed to the same conditions. But if you're close to the end of the row, you're going to be brighter. And if you're close to the middle of the row, you're going to be dimmer. If you're further out this way, if you place it next to a support post, you'll have a different shading situation than you will if you're halfway between support posts. So your placement, you end up needing to put a whole bunch of these reference modules in if you wanted to do a good job of characterizing what was available to the array, which is expensive and isn't usually how things work. So it also assumes that this sample module has the same bifaciality as all the modules that are in the system. But, they're very, very hesitant to be pinned down on what the bifaciality factor is. Most data sheets will say it's something like plus or minus 5 or 10% is what the bifaciality is. So even though you might characterize this reference the reference module very well, it might not be representative of what the array is capable of seeing. Okay, so let's take that go back to the sensor idea, and instead of putting it in the plane of the laminate, let's push it away from the plane of the laminate. Let's get it away from that purlin interference. Now we'll be measuring something that isn't affected by that aspect of the shading, but it'll still be affected by the torque tube. It'll still be affected by the rest of that uneven irradiance that you're seeing moving across the bottom, which would be okay if you were trying to do an evaluation over a long period. If you're trying to cram this capacity test into 2 or 3 days, it's not really very helpful, which is even exacerbated by the previous presenter saying, look at these half hour I've got at the beginning and the end of the day that makes sense. You could have a quite radically different rear side irradiance or very similar rear side irradiance and not see any variation that you're depending on for your regression in the test. So that brings me to my outboard measurement. So I've complained that no matter where you put it, it's always going to be wrong. It's going to be biased low. If you put it under the torque tube, it's going to be biased high if you put it out the edges. If you put it along the torque tube outside the array on the south end, you won't have a ground covered with shade, creating these large variations in illumination. It'll be a much more stable value, but you will pay for that advantage because the bias will be quite large. You can put a sensor in between the modules and get a reading of 60 watts per square meter. And you put the same sensor at the end of the torque tube and see 130 watts per square meter. So clearly there's a concern about depending on that value being a representation of the average But the out is that we're doing a capacity test. And the capacity test does this regression, and the regression can adapt and say, whatever's at that location corresponds to the power out. So you have a stable measurement and you have an average, basically, measurement coming out of the system. So you can create a regression correlation that'll identify how much power should come out if you put a sensor in this location. Which, okay, now you've got a problem because the model, PVSys, doesn't tell you what should be at that location. That, however, is just some math. I have some math to do that. We had 20 minutes to talk about this thing. So I decided not to present the math, but to present the answers without the math. So that's something we'll have to wait, but it's just math. I know. Okay. So this is taking the bifacial power flow and saying that the average rear POA is a challenge to measure. And so instead, I'm going to come up with this POA that's outside, but somehow can be correlated with what's in the model. So you create something that's measurable, something that's coming from the model that are supposed to agree with each other. So we have some data. I don't have the complete data, but this is correlating DC power, which could be considered representative of the average irradiance, subject to mismatch issues and things like that. Correlating that with the cell temperature. So I'm basically doing a power correction on the temperature correction on the power, the DC power, and just having two axes showing independently the front side POA and the rear side outboard POA. Well, in this case, not the outside. So this is the inboard measurement. And when you look at it, say, from above, you can see that you can confirm that this is not a straight line. The rear side doesn't go up when the front side goes up. It kind of goes differently, which is good because it makes doing regressions good, but it's bad in that you have to have another term in the equation. So going back to my previous, I've taken one term for POA and I've split it into two terms to regress on separately. As you can see, there's a dominant slope for the front side, and that goes so we can say the front side clearly affects the performance a lot, and the rear side has a small irradiance going from 10 to 90. This is the inboard measurement, and that correlates well, but it creates a slight tilt to this plane. So you have two separate correlation coefficients. Okay, I'm almost done. So I was just going to point out that the regression coefficient for the front is only is about 125% of the regression coefficient for the rear. And I would ordinarily expect like a 0.7 bifaciality plus some additional losses for the obstruction issues. And that's not quite happening here. So this is preliminary data. One of the issues that I have with the NREL data is that the sensors are placed in different rows. So this is correlated with row 2 power, which they're all supposed to be at the same position, but they don't necessarily have the same albedo underneath. And I think there's some local shading at one end. So I had to restrict some of the data. So this is unexpected. This is a little higher than I would have expected. I would have thought that the bifaciality would have pushed this down some more. And so far, we haven't concerned ourselves with the absolute bias to see when you actually wrap this up into the complete capacity test, how do things work out? Now, I've done this test before with the whole thing, but the answers I've been getting have been a little optimistic, at least my perception is. So I'm going through the motions correctly as I see them, but the results of the test are that it tends to pass a little bit more easily than I would have expected. That's the inboard. The outboard looks very similar. It seems to have a little bit higher spread on the data. And once again, all I'm doing is trying to evaluate how the sensor correlates with the overall average behavior of the array. In this case, because the outboard sensor has a large, has a bias, so you're getting like twice as much irradiance as you would in the middle, this coefficient is much smaller. Conclusions? There's been a lot of proposed methods, and my concern with some of them is that they don't address concerns that the investors have. I'm willing to trade a little bit of larger residuals for the ability to detect things that are poor design characteristics of the system. But this proposed method, I think, keeps the spirit of the original test. Okay.